All right, gang, here we go. This is for Chem 2, Unit 11. We're talking about titration. Specifically, we're going to talk about titration between strong acids and strong bases. All right, so we've kind of talked about titration before, and just hopefully you learned about this in Chem 1. But in general, titration is when you use a burette. Okay, this is a burette spelled like this. I've also seen it spelled like this. All right, and in this burette, you have a solution of known concentration. Now, this specific case, they're talking about sodium hydroxide, and then down here you have the solution of unknown concentration. All right, we call the known concentration is called the titrant. Okay, that's the fancy name for this, titrant. Ooh, titrant. All right, and then this stuff down here that we do, or the unknown here is called the analyte. Why are you doing that to me today? Analyte. All right. So that's your analyte. Titrant, it goes up in the burette. Analyte is what you're analyzing. All right. So the whole idea is that you can take a known concentration and then an unknown concentration, and by slowly adding the known to the unknown, you can figure out what the concentration of your acid or base that you started with. Okay. In this specific case, they're using a pH meter. Okay, that's primarily what we're going to rely on in our own labs. Okay, is using a pH meter. You'll also see, you probably have seen them done with indicators. Okay, and you use like a color indicator like phenolphthalein or bromthiamyl blue or something, methyl red, okay, in order to get a certain color, and when you reach that color, you've reached the end point. But here we're just going to be focusing on what's called the equivalence point, and in order to find that, we're going to primarily rely on a pH meter because they're a lot more accurate. Indicators also work, okay, and both of these are used to determine when the solution has reached the equivalence point, and this equivalence point is defined as when you've reached the point when the amount of acid in your solution equals the amount of base in your solution. Okay, now specifically, so that's the equivalence point. That's when that is true. Now, if we use an indicator, okay, an indicator, we have this other idea called the end point. Okay, and the end point is when the color change happens. When color change occurs. So ideally, when you pick your indicator that you need, or that you're going to use for your titration, you're going to choose an indicator that has an endpoint that's close to what you expect the equivalence point to be. And so then if you choose correctly, and there's lots of choices for indicators, we'll see them then, in a couple, or maybe the next video, all right? You'll see lots of different indicators, and if we choose correctly, then we can choose one where the equivalence point and endpoint are essentially the exact same thing, and we don't have to worry about it. So if we titrate a strong acid with a strong base, okay, so that means we're starting with, okay, starting this guy, all right, start, and then with just strong acid in our beaker, and then we're adding a strong base to it. All right, so if we measure the pH of this strong acid by itself, right here we'll be at some low pH, right? And that makes sense because, we've got just a strong acids completely dissociate, so we'll have a low pH. All right, and here, so in step number 1, we've got only hydrochloric acid present before we start titrating. Then we start adding our sodium hydroxide. So as we go from here to here, okay, we start adding our hydroxide, and so what occurs is it starts to neutralize that acid. So as the acid starts to get neutralized and turned into water, the concentration of our hydronium is going to go down. Now the interesting thing is, as we go this way here, our concentration of hydronium goes down, but it goes down very slowly. Okay, we've added from here to here, we've added 48 milliliters. Now we don't know exactly what the concentrations of these guys were, but we can assume we might say that they're about even. It doesn't really matter. But we've added 40 milliliters of our base, and look, and our pH has only gone up about, we're only like 10 times less acidic in 40 milliliters of titrant added. All right, then as soon as the H plus is completely neutralized, we skyrocket past this thing here, and where our slope reaches 0, okay, we call this our equivalence point. Now, when you're titrating a strong acid with a strong base, your equivalence point is always at 7. All right, so that's super nice. Your equivalence point is always at 7 when you're titrating a strong acid with a strong base. Okay, now, and we know this occurs when the moles of acid added, or the moles of base added equals the moles of acid that we started with. All right, and so when we're once again, the equivalence point is when those two moles are equal to each other, and that occurs when our pH is equal to 7. Once our acid is completely gone, when we keep adding base, our pH is going to skyrocket past 7 and become basic solution. And as we add base, we'll eventually level up or level off because the concentration of that base isn't really changing. Okay, so at the equivalence point, our pH equals 7. As more base is added, the pH again levels up. All right. This is going the opposite direction. If we titrate a strong base with a strong acid, okay, then our curve looks the opposite direction. We'd start off with a high pH, okay, because we're starting with a strong base, and then as we go down, we're adding acid to this, so the pH is going to slightly go down, but really for the most part be mostly level. And then once we reach the once we start to reach that point where the moles of acid, the concentration of our hydroxide is really, really low, and we've starting to balance out, we've reached that equivalence point, we get this sharp curve, and it's the exact opposite, almost flipped over. All right, and again, though, the pH is still going to be 7 when we reach that equivalence point, and that's always true when you're doing strong with strong. All right, so we're going to walk through a practice problem here with them. It says calculate the pH when 49 milliliters and 51 milliliters of 0.1 molar sodium hydroxide have been added to 50 milliliters of a 0.1 molar HCl solution. All right, so we can automatically say that we're going to be on either side of our equivalence point, right? Because we know the equivalence point is going to happen when the moles of acid and the moles of base are equal to each other. Since they have the same concentration, they're going to have that equivalence point is going to happen when you've added the same volume. So that volume, we started with 50 milliliters of 0.1 molar HCl, so we'd reach the equivalence point at 50 milliliters added of the 0.1 molar NaOH. So we're going to have one pH that should be lower than 7 and one pH that's higher than 7. All right, that's kind of what we're looking at here. So they're going to walk through this. It says it has to calculate the pH at 2 points. All right, the first point is just before the equivalence point, so the pH to determine small amount of strong acid that is not yet neutralized. The second point is just after the equivalence point, so we expect this pH to be determined by a small amount of excess strong base. All right, pretty much exactly what we said. All right, so here's the plan. For step A, as sodium hydroxide is added to the solution, the H plus reacts with the hydroxide to form water, and the sodium and the chlorine are spectators ions, and they don't affect the pH. All right, to determine the pH of the solution, we just have to determine how many of H plus were originally present and how many hydroxides were added, and then figure out the new concentration of H plus, take the negative log of that, and Bob's your uncle. All right, and then part B, going to do the exact same thing, but now we're past the equivalence point, so we're going to be finding the concentration of hydroxide instead. So first thing we need to do is figure out the number of moles of H plus in the original HCl solution. So all we have to do for that is just multiply our volume by our molarity, and we'll get this. So this is the amount of moles of H plus that we're going to use, right, that we started with. All right, and then do the same thing with our hydroxide. So this is the same thing with the hydroxide, and so this is the amount of moles of hydroxide that we added. Okay, and then we're going to use this new table we learned last video called the before change after, or maybe it was 2 videos ago. Anyway, so this is before the reaction occurs. It's in moles, so this is how much H plus and hydroxide we had. This is going to be the limiting reactant because it's smallest and it's a 1-to-1 ratio. All right, so all of this is going to go away, and we're going to be left with this much of this. All right. Now, in order to find the pH, remember the pH is equal to the negative log of the concentration. Well, this is just our moles, so we need to figure out the new volume. So we started with 50 milliliters of H plus right here, 50 milliliters of H plus, and we added 49 milliliters of the NaOH solution. So the new volume is 99 milliliters, so that'd be 0.0990 liters. So in order to get our new concentration, we need to divide our moles by our new volume. All right, so there's our moles, our new volume, and so our new molarity is this guy here. So then to get the pH, all we have to do is just take the negative log of that. And so our pH of our solution is 3. All right, so that's when we've added 49 milliliters of that base. All right, now we got to do the same thing for part B, but this is at 51 milliliters. Same sort of idea, okay? And but we got to find the volume. Here's the initial volume of H plus, same as it was before because we didn't change the amount of H plus. But we've added more OH minus, so now the OH is that. Our limiting reactant now, though, is our H plus because that's the one that there's less of, and it's still a one-to-one relationship to make this neutralization reaction. So there's 0 of this after the reaction's done, and 0.1 times 10 to the minus third of this. This is our new volume. Again, we got to find the new concentration, so we take our moles divided by the total volume, and so we get this as our concentration. All right. And then if we take the negative log of this, remember that is the concentration of hydroxide, so that's your POH. All right, and so the negative log of that would be 3. To convert it to the pH, we go to this. So it's kind of interesting. When we only added 49 milliliters of our solution, we were at 50. Or we were at 3 for our pH, and then when we added 51 milliliters, now we're at 11. All right, so we could kind of draw this like titration curve a little bit. So here's our pH. This is the amount of milliliters added, right? Okay, and so our pH, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I guess I misjudged. All right, so if we were going to sketch this out, we know that at 50 milliliters, we should be at a pH of 7. So 1, 2, 3, 4, 5, 6, 7. So we'll just mark that as 7. And so we should, that would be our equivalence point right there. All right, and up to that point, we're going to be acidic, right? 0.1 molar. So it would be, pH of 1 down here when we stop adding, and then it would be kind of like this. And we know at 49, so wherever that would be, 49 and 51, we know that that's equal to 3, okay, because we calculated that. And then that would be equal to our 11, so 14, 13, 12, 11, so somewhere out here, all right, like that, okay? And so our pH curve would do something like this, and then shoot up here, and then come out here again like that. Right, whatever, and that should be around 13 for that pH. All right. So anyway, so that's what our titration curve would look like, and then really though, this is really zoomed in, and so it's not quite as steep as it could be if I drew it a little bit more zoomed out. But anyway, so that's that. All right. Let's do a practice problem. Okay, it says calculate the pH when 24.9 milliliters and 25.1 milliliters of nitric acid has been added to 25 milliliters of a 0.1 molar KOH solution. All right, so again, this is really nice because the concentrations are the same. All right, so that makes it so we know for sure we're on either end of this equivalence point, because the equivalence point would happen when the moles are equal to each other, and we started with 25 milliliters of 0.1, so the equivalence point would happen at 25 milliliters of the nitric acid being added. All right, now we do know that we're starting with the base and adding an acid, so we're going to start, this is going to be flipped, right? The general curve of this guy should start basic and then go down like that. Our equivalence point should still happen at 7, though. All right. So let's give this a shot. So we know that the H plus that we add is going to be reacting with the OH minus, right? And that's going to be forming our water, okay? And so we could say that before, change, after, or BCA table here. I don't know. And what we need, remember for this, we're going to use moles. We don't use concentration, so we need to figure out the moles. So we need to figure out how many moles of our KOH we started with. Okay, all right, so we'll just take the 0.100 molar, okay, and we're going to multiply that by the liters that we have, so that would be the 0.0249. Remember, molarity times our liters is going to give us moles, so we say, well, shoot, I don't need to type that into my calculator. I can do that one in my head, so this would be 2.49 times 10 to the minus third. All right, so that's our initial concentration of KOH. All right, and then we can do the same thing here for the nitric acid. But it would be, oh, this is for the nitric acid. My bad. This is for the nitric acid, and so then this would be for the that'd be for the KOH. Sorry. So moles. I'll label this. Come on, moles, HNO3, and this would be 2.50 times 10 to the minus third moles of KOH. All right. So, and because these are both strong and they're 1 to 1, they're going to produce one of these. So the moles of nitric acid is equal to the moles of H plus. So that'd be our 2.49 times 10 to the minus third. All right, and this will be 2.50 times 10 to the minus third. And we're going to have, it doesn't really matter what this is, all right, because it's not going to be, it doesn't really matter how much of that we make, but, all right, so that's 0. But anyway, so this is going to, we're going to lose some amount of that, 2.49 times 10 to the minus third. All right, and we know we're going to lose that much because that's our limiting reactant right here. So, and then, and this would be minus 2.49 times 10 to the minus third. And we know we're going to lose equal amounts of those things, right? And so that's going to be equal to 2.49 times 10 to the minus third. But really, this doesn't matter because there's, gobs and gobs of moles of water in there anyway, compared to the other things that are reacting. So this will become 0, and this will become 2.5 times 10 to the minus third minus that. So it'd be 0.1 times 10 to the minus third, right? And 2.49 times 10 to the minus third. All right. So then, in order to calculate the pH of this guy, well, this is the concentration of hydroxide. So our pH, okay, is going to be equal to 14 minus the negative log of what we just calculated, because that's the concentration of hydroxide. So 0.1 times 10 to the minus third. All right. So we say 14 minus the negative log of 0.1 E minus third. All right, and so I got a pH of 10, and that makes sense because it should be basic. Okay, then we can do the same thing here, but for the other guy, for our part B, so we have our H plus OH minus, all right, and that's going to form H2O. All right, and then we got our before, change, after. All right, but we need to figure out the number of moles we start with. Well, the number of moles of KOH is the same, so we can skip that stuff. That's going to be the exact same. That's still 2.5 times 10 to the minus third. And hopefully you realize that if we multiply this by 0.0251, that we'll get 2.51 times 10 to the minus third. All right, you can double check that. So you multiply your volume times your concentration. All right, so we're going to lose the limiting reactant amount, so that's the 2.50 times 10 to the minus third, and we're going to lose the limiting reactant amount times 10 to the minus third. We started with 0 water. We're going to gain some amount. We're going to gain the amount here, 2.50 times 10 to the minus third. Again, the water doesn't really matter. You could practically skip that for these kinds of problems. So this would become 0.1 times 10 to the minus third, right? And then subtract that out, so that's 0, and then 2.5 times 10 to the minus third. All right, so our pH here, well, this is our concentration of hydronium, so that just be equal to the negative log of 0.1 times 10 to the minus third. All right, and so that should just be 4, right? I guess I could double check it, but I'm pretty sure. Yep, cool. And so, and now we can see that, on either end, we'll be, when we're 0.1 milliliters away from our equivalence point, we'll be at 10 and 4. So you can see it jumps pretty dramatically. All right, so that's how you do titrations for strong acids, strong bases. And really, first step is figure out where your equivalence point is. Okay, second step, just do your neutralization, figure out how much moles is left. And you can do it with your before change after table like we've been practicing here, or you can just do stoichiometry like we did way back in Unit 3. All right, so anyway, so it doesn't really matter. Just, work it how it makes sense to you, and just make sure you do it right and double check everything. Let me know if you have any questions, and I'll see you on the flip side.